Let's have a look at this infinite series, double series. First, we sum with regard to n. We have k squared times n over 3 to the k times n times 3 to the k plus k times 3 to the n. Then we sum with regard to k from 1 to infinity. So first of all, suppose it has a limit, right? What the limit could be. So it's denoted as s. So here's the trick. First, I'll multiply top and the bottom by n at the same time. Right, so that becomes infinite sum. We have k squared times n squared. We have n times 3 to the k times n times 3 to the k plus k times 3 to the n. Right? So this time it looks like more symmetric. N 3 to the k, n 3 to the k, 3 to n. So this time we can simply re-index it. First we sum with regard to n, then we sum with regard to k. If I just switch n and k, right? K first, then n, then I should rewrite n as k as n, then it'll be the same. Right? I change them at the same time because it's a dummy index. Right? So first of all, it becomes n equal to 1 from infinity, k from 1 to infinity. Right? Then k becomes n becomes k times 3 to the n times k times 3 to the n plus n times 3 to the k. Right? Like I said, it's a dummy index, exactly the same sum. But the question is that from this onwards, can I simply change the order of summation? Because from this step to this step, I'm not changing the order of summation. I'm simply changing the index, right? Re-indexed. Therefore, I switched the variables at the same time. So from here, can I simply first sum with regard to n, then sum with regard to k, without changing the variable, right? Keep this. So the answer is yes, it's justified. And I'm going to go through the justification after I complete calculation of the s. Right? So from this onwards, like I said, I'm going to add s plus s, right? This plus this. Because right now I have exactly the same summation, same index. So 2s is equal to k from 1 to infinity, n from 1 to infinity. All I need to do is to add up the summands, right? This and that. Notice the common factor is this, right? K squared, n squared. Down here I have exactly the same n 3 to the k, k 3 to the n, right? n 3 to k, k to 3 to the n. So k squared, n squared, n 3 to the k plus k 3 to the n, common factor. Then I have 1 over n 3 to the k plus 1 over k 3 to the n. I can simply combine common denominator, and up here I have k 3 to the n plus n 3 to the k. Right? This is my summand. So simply here I have exactly the same down here and up there. Right? Simply cancel. Right? I simplify further. 2s k from 1 to infinity, n from 1 to infinity. And I simply have k over 3 to the k and n over 3 to the n. Right? So since I'm summing with regard to n, then it has nothing to do with k. So I just pull out all the k terms. 2s equal So S equal half k from 1 to infinity. Pull out the k terms. K over 3 to the k. Then n from 1 to infinity. N over 3 to the n. And this should be easy to work out, right? Since t equal to n from 1 to infinity of n over 3 to n, since I multiply 3 on both sides, 3t is equal to n from 1 to infinity, n over 3 to n minus 1. Right, but so here I just re-index again. N starts from 1, so n minus 1 starts from 0. So n starts from 0 to infinity. Here I have 3 to the n. The top I start from 1. Here I start from 0, so n plus 1. Right, still starts from 1. Right, here I just pull out the 0th term. 0th term is 1 over 1. Then n from 1 to infinity. N plus 1 over 3 to the n. Right, that's 3t. So if I subtract, becomes 2t is equal 1 plus, this time exactly the same index, from 1 to infinity. Then this minus that. So 1 over 3 to the n, right, that is geometric sum series half. Right, so t should be equal to 3 over 4. Right? S should be equal to half k from 1 to infinity. Right, so I just worked out this one. Right, 3 over 4 multiply out, so 3 over 8 down here. Right? Then k over 3 to k, which is exactly the same infinite series as the one I just worked out, right? 3 over 4. So that's 9 over. Now let me justify why we can interchange the summation. So when you look at the summand, right, you can treat it as if it's a function of two variables. Two variables happens to be natural numbers. Then we can denote it as AKN or AIJ. The same thing, right? Real numbers. And have a look at this infinite matrix. A11, A12, A13, all the way. Second row, A21, A22, A23. Third row, A31, A32, and A33, all the way, forever, infinity. Now, imagine if the first row, right, the first row series is somehow convergent. Then you can say, okay, fix row number 1, right? Just like in here, you first of all you fix k, then you let n, right? N from 1 to 3 to infinity. Then you work out the sum of each row. Then you add them up, right? That's the outside sum. So under one condition, it can be justified, right? The same as if you add up the first column, add up the second column, add up the third column, then you add them all up. It'll be the same. If we have this condition, if we resequence this infinite matrix using C, right? Call this C1, perhaps this C2, C3, C100, all the way, right? If Cn absolute value, the series is convergent, absolutely convergent. Let's call it C, where Cn is any sequence of this infinite matrix. The reason is because, according to the definition, given any epsilon that's positive, we can have this absolute value of n from 1 to capital N. There is a capital N that's big enough of Cn absolute value minus the limit C. Right? But remember, C is in fact the infinite sum from 1 to infinity. Cn absolute value. Alright, so you have this finite sum that is infinite sum. So 1 to capital N, 1 to infinity. Then the remaining term has to be, it's already positive, doesn't matter. So absolute value. Right, the remaining term must be from capital N plus 1 to infinity. Right, because this from 1 to 3 to capital N, that is 1 to 3 to infinity. The difference has to be the next capital N plus 1 to infinity. Right? Absolute. It's already absolute. Absolute value. Now, according to definition, right, given it must be smaller than epsilon, perhaps half of epsilon. Now, this is going to be helpful because once we have a look at this whole C1, C2 all the way up to C capital N, capital N might be very big, but there is still finitely many C's in here. C1, C2, whatever, all the way up to C capital N, right, finitely many. Then we can extend it all the way to A1N, extend it all the way to AM1. Some rectangle matrix that's big enough that happens to cover C1, C2 all the way up to C capital N. This is definitely doable, right? So M is big enough, N is big enough, right? PQ are some fixed natural numbers. Now, then we can have a look at this here is, I'll write it up here. This finite J from 1 to N, I from 1 to N. In other words, absolute value. Right, add absolute value to each term. We have a look at the sum of this finite rectangle big enough matrix. This one. The difference is minus this N from 1 to capital N, finitely many C's. Absolute value. When you have a look at their difference, right? Because like I said, this big enough rectangle matrix already covers C1, C2 all the way up to C capital N. So the remaining term, when you subtract, the remaining term has to be the rest of C's. Because C1, C2 all the way up to Cn, they're all gone after we subtract. Right? And also remember Cn is a resequence of this infinite matrix. Right? So what you have left is just n from, you're going to start from capital N plus 1, not to infinity, but to some finite n naught. N naught may be 2 million, whatever, right? It has to be a finite number. Right? So you have finitely many terms here. Must be no larger than n from 1 to infinity, right? This is definitely, hold. Then this, like I said, from n from same, capital N plus 1, right, to infinity, right? This no larger than this, no larger than half of epsilon, right? Half of epsilon. Right, this is finite in many terms. This is from the same starting point, but to infinity. And so here we're going to apply the triangle, before we apply the triangle formula. So here is the already positive, right? Already positive. Maybe, same thing, absolutely. But let's rewrite this term. Right? This term, in fact, can be written into, remember, right? This minus this is equal to this. So this term is this term. So this must be written, like I said, because this from 1 to capital N can be written into n from 1 to infinity minus n from capital N plus 1 all the way to infinity. Right? That's finitely many terms starting from 1. That's all the terms that is starting from capital N plus 1. Right? This has to equal to this. Right? So, in other words, this is in fact C, the limit C. Right? So let's rewrite this. You have the finite sum I from 1 to n. Then you rewrite that. C minus become plus Cn n from capital N to infinity as a value. Right? Then you can apply triangle inequality. Right? So split this absolute value minus absolute value. Then this will become, right? This will become smaller. Like I said, you just minus absolute value. You don't even need absolute value. It's already positive. Right? Called triangle inequality. Now, this time let's just move this term over to this side. Right? So this stays. Aij. There's absolute. I almost forgot. J from 1 to n. I from 1 to n. Minus C absolute value less than or equal to. This term now from here. So half epsilon plus Cn n from capital N plus 1 infinity. And this, like I said, this, right? Less than half epsilon. So half epsilon plus half epsilon. Right? So that's exactly the definition of the limit of this one. Is exactly C. Right? The distance is arbitrarily small. Right? So like I said, when m and n are big enough. Right? So this means first I sum with respect to j. J is the column. So I sum this row, sum this row, sum this row, then add them up. Right? If you do the same, apply the same method, it'll be still true. If you sum this column, sum this column, sum this column, and add them all up. And the plus, if you have a look at this first row, if you add absolute value each one, right, the series of the first row has to be convergent, because no matter how many terms you add in the first row, absolute value, it's no larger than all the C's, right? All the C's, they're no larger than this. After adding absolute value, you have a non-negative series, which is bounded above. So it has to be convergent. Same is true for each row, right? So therefore, you can keep m, you can let n approach infinity, right? Inequalities still hold. Perhaps let's rewrite. After you let n approach infinity, you keep j, or keep I, keep m. So j has nothing to do with j anymore, right? J is a dummy index, right? N approach infinity. So for each fixed I, we have a Si. S1 is the limit of the first row series, right? Absolute value series. Right? Since it's absolutely convergent. So without absolute value, of course it's convergent. S2, for example, is the limit of the second row, the series absolute value limit. Then I from 1 to n. Still true. Then you can, like I said, you will work out the sum of each row, then you add them all up. Still going to be convergent, because again, it's no larger than all the terms of C's, right? Still bounded above, right? Non-negative series. You let m approach infinity. It's still going to be true. Right? It'll become a constant, some d minus c. Right? Since epsilon is arbitrarily small, so d must equal to c, right? Otherwise, it cannot be arbitrarily small. So this justifies, like I said, if you do it the other way, right? It's still going to be the same result. So we can really, safely interchange the summation. So finally, we have to make sure that our, if we treat it as an infinite matrix, right? Treat it this one, right? Perhaps k is the number of row, n is the number of column, so a 2, 3, so k equal to 2, n equal to 3, so on and so forth. So we have to make sure that if we select any random, if we can find some Cn, which is a sequencing of this infinite matrix where it is absolutely convergent, the series, then we can interchange. Right? So the question is, can I do it like this? Can I do diagonal sum? This plus this plus this plus this, this, and so on and so forth. Diagonal. Right? So when I'm doing diagonal summation, I say, as long as I can show, so C1, C2, C3, C4, C5, C6. Right? So if I do it this way, so I must do, first of all, I have to make sure that I plus j equal to k. Then k goes from, for example, if it's this diagonal, right? 1 plus 2, 2 plus 1 equal to 3. 1 plus 1 equal to 2. Here, this one, this one, this one. 3 plus 1, 1 plus 3, 4. 2 plus 2, 4. Right? So 2, 3, 4. So k from 2, 3, 4 all the way to infinity. Right? I plus j equal to k. For example, 1 plus 3 equal to 4. 2 plus 2, 4 equal to all the diagonals. So, okay, so this one. So I squared times j. 3 to the I times j times 3 to the I plus I times 3 to the j. If I do it this way, can I show that absolute is already positive? Is it convergent? If it's convergent, then we can interchange. So the thing is that here, I'll just loosen it a little bit. Loosen the inequality. K from 2 to infinity. I'm going to replace I with K and J with K as well. That's okay. K squared times K cube. Okay? And let me, because you notice that down here is just exponential, which grows much faster than power, right? So I can just I can do this, expand it first. So j times 3 to the I then square plus I times 3 to the I times 3 to the j. 3 to the I plus j. I plus j equal to k. So 3 to the k. All right, no problem. Now I can simply see that all I need is this one because I know that exponential grows faster than power. I don't even need this one. Right? Make it bigger. I'll just get rid of all this thing. Right? Becomes this. I'll just replace I with 1. I start from 1, 2, 3. I just make it smaller here. Only keep this one. I've made it bigger, loosen. Of course, here we have I plus j equal k. K from 2 to infinity. Yeah? Don't forget that. So in this case, I have I plus j equal to k. Right? If k was 4, then 1, 2, 3 terms. So k minus 1 terms. The same, every term is the same, right? K minus 1 many terms. Every term is the same. So this doesn't matter either because right, it's just power, k to the power whatever, 4. Right? Cannot grow faster than 3 to the power k. Right? This grows much faster. So without even getting to details, I can already see that this already converges. Right? So yes, it's really condition satisfied. So really we can interchange.